Hi, welcome to Unit 1.2, Foundations of Chemistry. In this note video, we'll be focusing on the second half of the first key question in this unit, which is how do we represent matter? This video has been broken into parts A and parts B. This is part A. Just a quick note, make sure with this video, as with every other video, you annotate key information or anything that's not shown on your slide packet. And also that you'll have to watch 2 additional Lewis structure videos. So let's begin. Okay, so real quick, why is it important for us to go through these different representations of matter? It's because we utilize these sort of visuals to make sense of chemistry, and there are many different ways that, or many different types of visuals or models that we use, and that depends on the purpose for which we intend to use them. All of these models have limitations. That means that you are going to have to utilize all of these models in some way. So it's important to just sort of see what they are all together, because sometimes you'll have to translate from one to the other. And I hope that you'll find going through these basic representations helpful. So here are the 6 basic representations. We will not be covering in any of these videos A or B chemical names because we've gone over that separately. But the other forms 2 through 6 we will be. In video A, we're going to focus on atomic symbols, chemical formulas, and Lewis dot structures. So going into atomic symbols, here's a general atomic symbol, and you'll have the, of course, element symbol in the middle, and then to the lower left you have the identifier, which is the atomic number. It tells you the number of protons. I call it the identifier because you can use the atomic number to identify what the element is, since, for example, all hydrogen atoms, only hydrogen atoms have 1 proton or atomic number of 1, and all oxygen atoms and only oxygen atoms have 8 protons or an atomic number of 8. So we can use that number to just identify what the element is. In the upper left you have the mass number, which is the number of protons and neutrons. I put here the element symbol from the periodic table just to note that the mass number, when you add up the number of protons and neutrons, should be a whole number, but in the periodic table there's this number with the decimal, so how are these two numbers related? This number is called the average atomic mass, and it's the average mass for all the different types of isotopes. So elements all have the same number of protons, but not the same number of neutrons. Therefore, they'll have different masses. And when we average the naturally occurring isotopes in the world, we're going to get some sort of decimal here. So that's where this number comes from. However, even though the average atomic mass and the mass number are not the same, they're approximately the same. So what you can do is you can determine the mass number for the most common isotope by just rounding this number to the nearest whole number. So here for nitrogen, we would round this to 14. The last piece of the atomic symbol that is important is the charge. It's the number of protons minus the number of electrons. Protons have a +1 charge and electrons have a -1 charge. So when you have the same number of protons and electrons, you have a neutral species or something with a charge of 0. If they're not balanced, then you're going to have something with a positive or negative charge. When we call those anything with a charge, we call them an ion. So here's just a couple of quick examples of how we can go from information like the charge, atomic number, and the mass number and draw an atomic symbol. So if you're given a charge of -1, an atomic number of 16, and a mass number of 33, first thing you want to do is figure out what element it is. So for that, you should use the atomic number. So if its atomic number is 16, we know it's going to be sulfur. We can draw that symbol. Then we can just go plug in everything else. Atomic number lower left, mass number upper left, charge upper right. For the second example, we're given the subatomic particles. For this, what we're going to need to do is, again, we're going to start with the number of protons or the mass or the atomic number to figure out what the element is. So if it's 18, it's argon. And then we can go ahead and put it in our atomic number, the lower left. For the mass number, which is in the upper left, we have to add the neutrons and protons together, which will give us 35. And the charge will be protons minus electrons. Since the protons and electrons are the same amount, the charge is 0, so we can just leave it blank. Alright, go ahead and take a moment to try this CFU. When you press play again, the answer will be revealed. Great, so if you have any corrections to make, please make those on your packet. We're going to move now straight into the chemical formula. The chemical formula tells you two things: the number of atoms in one molecule. So if we look here, we see we have 1 magnesium, since the subscript is an invisible 1, 1 carbon, since the subscript is an invisible 1, and 3 oxygens. It also tells you the molar ratio of atoms. So in 1 magnesium carbonate molecule, I know that there is 3 oxygen atoms. That means it's a 1 for the whole molecule to 3 ratio. It also tells you the ratio of atoms. So for example, here there's a 1-to-1 ratio of magnesium to carbon. Now, we can utilize that understanding of chemical formulas for what's something called the empirical formula. Empirical formulas, you'll see later, is useful for something called elemental analysis. But for right now, let's just go through the definition of what an empirical formula versus molecular formula is. Molecular formula is the chemical formula for the entire molecule. So far, you've been looking only at molecular formula. It tells you the total number of atoms in the molecule. The empirical formula gives you the smallest whole number ratio. So if you look at the molecules below, you will notice that you can actually simplify the ratios here to smaller numbers. And all 5 of these molecules have a 1-to-1 ratio of carbon to hydrogen. And just a quick note here that if you tried to count it out, you would maybe think that there's a couple of carbons or hydrogen missing. These are organic representations, and oftentimes the carbons and hydrogens are not drawn in, certain ones. So I'm just going to put them in just so that you see them. If it's helpful for you, where I've drawn them in red, you should draw them as well. Okay, so empirical formulas again are the smallest whole number molar ratios. So here's the CFU. You're going to try and figure out which one of these molecules has the same empirical formula as acetic acid. Quick suggestion, I would first find the empirical formula for the molecular formula for acetic acid and all of the other ones, and then write their empirical formulas and see which ones match. Okay, so here are the answers for that. So acetic acid has a molecular formula of C2H4O2. If you divided each of these by 2, it will simplify to CH2O, and that's how we get the empirical formula. And the same thing is true for A and in choice C. They all have the same empirical formula as acetic acid. Alright, last one we're going to go over is Lewis dot structures. It's used to predict bonding in molecules and explain phenomena associated with bonding. So there are 2 types of methods for drawing Lewis dot structures. The unpaired electron method, which was what we've learned in school. That's a great method for conceptualizing Lewis dot structure, but it can be limiting. So we're going to use what I like to call the banker method, which is instead of focusing on trying to pair up unpaired electrons, you're throwing all of the valence electrons in this big pot or this big bank, and every atom that needs them to get the full octet will take them out as necessary. So there may be some sharing, you may have some lone pairs. And this method is actually quite easy and very useful. So since there are many good videos that show this, I'm not going to show this in this video here, but I have linked in this assignment the videos for the Lewis dot structures. You're going to pause this video now and watch those 2 videos, and then come back and we'll look at how to apply Lewis dot structures. While you're watching the videos, be sure to take notes on steps for drawing Lewis dot structures and calculating formal charges. Alright, here are some key points from the Lewis dot structure video that you, or Lewis dot structure notes that you should get. 1, Lewis dot structures show the arrangements of valence electrons in a molecule, and it is based on pairing unpaired electrons. There's something called the Hunk 1, 2, 3, 4 rule, which basically says that hydrogen, since it has one unpaired electron, wants to form one bond, it usually forms one bond. Oxygen 2, having two unpaired electrons, forms two bonds. Nitrogen 3, and carbon 4. So these tell you the common number of bonds you will find in each of these. Now, from these Lewis dot structures, we can determine what's called formal charges and draw resonance structures. We won't go into drawing resonance structures at this moment, but just know that that's something that you can do from Lewis dot structures. I also want to quickly point out Lewis dot structures of ionic compounds. This may not be clear on your packet, so anything that's not clear, you might want to make it clear, like the charges, etc. But the main thing is, in an ionic compound, instead of sharing electrons, the metal gives up its electrons to the nonmetal. And so that means the metal is going to become positively charged and the nonmetal negatively charged. And in Lewis dot structures, we draw brackets. We oftentimes draw brackets around things that have charges. So this is what it looks like for an ionic compound. Now, here's a CFU. You have three species. You're going to draw the Lewis dot structures and write formal charges for any atom without a zero formal charge. Pause the video now. When you press play again, you'll see the answer. Great. So here are the answers for the three. If there are any corrections that you need to make, please make it now. And I just wanted to point out that that either one of these would be fine, but these are all resonance structures of NO3, and they're known as resonance structures because essentially what happens is the placement of the double or triple bonds could shift, and also the charges could shift, but the overall skeletal structure remains the same. Okay, so here are some uses for Lewis dot structures, a way we can apply Lewis dot structures to make sense of things. We can use them to predict the most stable resonance structure. And in this example, it's asking which one of these is the most stable resonance structure. Because applying the Lewis dot structure rules, you could technically draw this molecule either of these three ways. So which one's the most stable? Couple rules. You want to make sure every atom has an octet. Exception, of course, hydrogen and boron, and you can have expanded octets. They're okay for any element in period 3 or higher. You want to make sure that you minimize the amount of formal charge on any species, and negative formal charges, you want to try and put them on the most electronegative atom. These rules are in order of priority, so you want to focus on giving every atom an octet, and you want to focus on minimizing the amount of formal charges. So the answer for that one was choice B, and that's because all of the atoms have a zero formal charge here, whereas these, they have formal charges. So B is the most stable. Okay, this is a little cut off, but it says Lewis dot structures to explain the trend of bond order versus bond length and strength. So if you look at the single, double, and triple bond, the average bond length, it decreases going from single to triple, and the energy to break that bond, or bond dissociation energy, increases. So that says the strength increases from going from single to triple. And so these are really important trends that we need to know, because they'll help us to make determinations on what a species is. The bond length and strength trends we'll explain a little bit more about in class, but all of that should kind of make sense because single bonds, the atoms are farther apart, and as you pull them in, and reinforce the bond with double or triple bonds, you'll make them come in closer. You can use Lewis dot structure to explain data like this involving resonance structures. So here, oxygen O2 has a double bond, and hydrogen peroxide has a single bond. The bond length of oxygen is 121, and for peroxide is 148, but ozone is in between. So why isn't that? Why isn't there two, one for the single and one for the double bond? That's because in a resonance structure, they don't exist separately. They are kind of blended or averaged together. So this is not a double bond. This is not a single bond. It's like a 1.5, an average of the two. And so the bond length is going to be between the length of a double and single bond. So now this is the last CFU, CFU 4, which oxygen-oxygen bond is easier to break. You're going to base it on the trends with double, single, triple, bond length and bond strengths. When you press play again, the answer will be revealed. All right, here is the answer. If you have any questions, let me know. And I hope you all have a quality day.